All right. Good evening, folks. So it looks like no one's in here tonight, but I do have some questions that I think we can go over from the book so that you guys can better understand what's going on in chapter 7.5. Yeah, let's get started. Okie dokies. Let's start with problem number 5. All right, so we're given the probability of event E, which is equal to 0.4, the probability of event F, which is equal to 0.5, and the probability of E intersecting with F, which is 0.2. So our goal is, what we want to do is find the probability of E union F. Okay, well, first of all, I think we need to ask, what does what does each part of this mean? For instance, what does E intersect F look like? And so basically that is what is in common. And this is everything in both. Because remember back in 7.1, we would talk like if E was a set that looked like, and F was a set that looked like this. Then E intersecting with F would be all of the ones that they had in common, or everything that was the same between them. In this case, it would be B and D. But E union F would be a little bit different because it would be everything in these. So it would be all of them. But notice that there is only one B and one D. You don't end up counting that twice, even though it is in both E and F. So what we're given is what they have in common, but we have to make sure that we take into account that they do have something in common, given by this. So basically how I solve this problem is I set it up like this. We need to find what's all inside. So I had the probability of E plus the probability of F minus the probability of the two being the same, which is equal to the probability of. How do I know this is true? Well, we are given in the book an equation, which I believe is, let me find what page that's on. We are told in the additive rule, this is equation number 3 on page 394. So we're told so in the book, but why does it make sense? Another kind of like little superfluous example. What if I had 10 numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I am trying to figure out what the probability is I pull E. And the probability of pulling E, I'm going to call E, we have 0.4 here. So 4 of these numbers are going to be E. So this is my E. Then I'm going to think about my F, and I know that I have 5 numbers inside of my F, and I know that 2 of those numbers are the same as E. So I'm just going to randomly pick. I'm going to say it looks like this. So there's 1, 2, 3, 4, and 5 numbers in my F. So how many total numbers are there in this set from E and F? 1, 2, 3, 4, 5, 6, 7. So there are 7 numbers. So the chance I pick something that is in E or in F is going to be 7 out of 10, or 0.7. So that's kind of how I started like thinking about this problem. Asking myself, like, if I just had like 10 numbers and I had a 1 in 4 chance of getting E, which is this group here, and a 1 in 5 chance of pulling one of them that was in F, which is that group here, and I know that there are 2 overlapping, which is this here, how many numbers total are there? So this equation does make sense, and it's something that you can kind of like figure out if you don't necessarily remember it, for instance, on the exam. Okay, that being said, we know the probability of E, which is 0.4, the probability of F, which is 0.5, and we know the probability of E minus F, or excuse me, the probability of E intersecting F, or the probability that you pull something that is in both E and F, is equal to 0.9 minus 0.2 is equal to 0.7. So a 7 out of 10. And that matches up with what I got up here from my little thought experiment as to like what I would end up getting. And of course, this isn't exactly how like this problem would go in reality. We wouldn't know which of these numbers were a part of E, but it's just how I kind of like structured my thought process about the what's going on here. Okay, so we did 5. I would like you guys to take a second and try to do number 7. Pause the video if you'd like to. I'm going to work through it in a couple seconds. But yeah, go ahead. Try number 7. Okay, so I'm assuming you paused the video or at least thought about the problem. So we are given this time the probability of E union F instead of intersecting. So we switched up what we wanted. So we don't have what we're going to end up doing is using equation 3, but we're going to have to rearrange it. So what we're given for equation 3 looks like this. And all of these are just going to end up being numbers. So what we can do is we can add whatever this number is to both sides. And we can subtract this number from both sides. Which gives us a whole new equation that we can work with, which looks pretty similar to the other one, but the intersection and the union have switched places. So we can just use this equation. That being said, let's go ahead and put the actual numbers in. We have PE equaling 0.7 plus PF equaling 0.5 minus 0.8 is equal to PE intersecting F. And just work this out, it's 0. Oops. 1.2. I guess I can't add. Not today. So it's 1.2 minus 0.8, which is equal to 0.4. And that's our answer. If you don't want to look at all of this stuff going on up here, what you can actually end up doing is just put the numbers into the equation that we have, equation 3, which again this is the intersection of F. This is what we used for number 5. We can say this is 0.5 minus, or excuse me, 0.7. I jumped the gun a little bit there. 0.7 plus 0.5 minus, and we don't know what this is, so I'm just going to leave it as the probability is equal to 0.8. And then we can like shuffle these numbers that are maybe easier to move around. Anyway, so just another like thought process question. Is this mutually exclusive? Are these events, E and F, are they mutually exclusive? Give you a second to think about it. And the answer is no. Why? Well, logically speaking, we know that there is a point, there are a probability, because we know that the probability of saying that E is intersecting with F is equal to 0.4. So if there's a probability of that, then there is intersection. And if the intersection exists, then by definition, they are not exclusive. All right. Let's try number 15. All right. So again, I would recommend just going through and trying the problem beforehand, just to see if you like have a handle on it. See if you can do it faster than me. Okay. So we have A and B, which are two mutually exclusive events. And they're in the same sample space. That's just kind of a given. We know that the probability of A is equal to 0.6. The probability of B is equal to 0.2. So we need to find a bunch of different things. We're going to start off with the probability of A intersecting with B. Okay. How can we find this? Because there's no probability of A being A union B. How do we find this? Well, we're given in the problem that it is mutually exclusive, which is just the way of the problem telling you that for sure the probability of that happening is 0 because A intersection with B does not exist. There is no instance where A, for instance, if we had an A here, it would be A and B, and B would be C, D. There is no intersection. Doesn't exist, so the probability of picking something that doesn't exist is 0. Okay. Give me a sec to erase this. Okay, so that is A. And from that, we can start to find other stuff. Okay. I'm just going to write down. All right, so that's part A. Okay, so part B. Now we want the probability of A union B. Well, we know that there are no intersections. That is told to us by part A. So we can basically just say that because they're mutually exclusive, the probability of A plus the probability of B is equal to the probability of A or B. So I can pick something from set A or something from set B. So that would just be 0.6 plus 0.2, which is equal to 0.8. Okay. All right. I think the biggest problem for me, at least while doing this chapter, was dealing with all of these different, like, what is the difference between, that doesn't make any sense what I just wrote. Clearly I'm a little bit confused. What is the difference between this and this? What do they mean? I kind of established it like kind of firmly as I was doing these problems over and over again, that when they say this, they mean anything in A or B's repertoire, but this means that it has to be something that is in both set A and set B. So it's where they intersect, the probability of pulling something that they have in common. Which again just comes about with practice, being able to intuitively look at that and say, oh, that's probably something like this. Okay, so pulling onto some notation from section 7.1. So we have this. What does this mean? Well, this means the probability that it's not one of A or B. So that's what this bar is telling us. That being said, how do we find that? This is a tool that they're often going to use either using notation like this or in a like exam or on a quiz. They'll have it like everything but or something like that. And so there's some word clues that you can start to pick up on inside like word problems that basically tell you what you need to do is find 1 minus the chance of something happening. So the chance of getting something that's in A or B is this, and the chance of not getting something in A or B is this. So that's going to end up equaling 0.2. How can we check to make sure that that's right? Well, the probability of getting something inside A or B plus the probability of not getting something inside A or B is going to be equal to 1, which is the probability of getting something, or for sure drawing something. It's either in A or B or it's not in A or B. And so we add these two together, and that checks out. So we know that this makes sense. If this number was not 1 when we added it together, then we would have known we've done something wrong. Anyway, so that's how we get this equation up here. Okie dokies. So that is C. Let's talk about D. This is the probability of B naught. So we want everything but B. So anything that is not in the set of B. And so once again, like we did in part C, we're going to say that 1 minus the probability of getting B is equal to the probability of not getting B. And that is going to be 1 minus 0.2, which is equal to 0.8. The probability of not getting something inside of B is 0.8. Okay. Continuing, we have E. The probability of not getting something in A, same process. So 1 minus 0.6 is equal to 0.4. Okay. And finally, F. Probability of A intersecting B not. Well, if we follow the same pattern that we've been doing for the rest of these knots, it's going to be 1 minus the probability that A does intersect B. And we know from up here that the probability of A intersecting B is 0, and that makes perfect sense. So the probability of A intersecting B is equal to 1. That means that every time we draw, if we have like 10 numbers in a hat and we draw a number and there's numbers that are a part of group A, like say group A is even and group B is odd, we can never draw a number that is both even and odd because numbers are even or odd. There is never any even and odd number. So if A is even, B is odd, A intersecting B does not exist because there are no numbers that are even and odd. So every time we draw a number, it will be even or odd. And that's what this whole section is kind of saying, is that because the intersection doesn't exist, the probability is 0, so the probability of the reverse of that is 1. Okay. Whew. All right. If this was not mutually exclusive, if this was a number, then you could solve, if this, for instance, was 0.1, so not mutually exclusive, then this would be 1 minus 0.1, and you can solve it in the exact same way. All right. I feel like I had something more to say about this, but I guess that will be it. Oh, just kind of like reiterating again that this notation, like something that's very important for you to be able to do is move between notation, word problems, and numbers. And just like interchange between all of these so that you can like better like assess a problem on an exam. Okay, let's do problem 17. Okay, these are kind of like a formula that is given to you when odds are for or against something. And I would again recommend doing just like a bunch of these just to get used to like what it feels like to read the problem and then what are they asking you for. We are given that the probability is 3 to 1 for event E happening. And so we want to put that in a different way. We want to find like a number that represents that. So the probability of E is equal to 3 over 3 plus 1, which is equal to 3 over 4. Which is equal to 0.75, which is equal to 75%. So there's a bunch of different ways to write this. All of these are technically correct. This, and this, and this. They're all right. They're all describing the probability that E happens. So yeah. If we look at 19, the odds are now 7 to 5 against. If they're against E happening, then E is going to be this lower number. Like it's less likely that E happens than like not happens. So that would be 5 over 7 plus 5, which is equal to 5 over 12, which is the probability of E happening. Notice that the probability of E not happening is greater, not equal to, greater than the probability of E. And that's kind of like what you can kind of see here because we have 7, which is bigger than 5. Okay. So I think that the last problem that I am going to do tonight is going to be this whole sequence of 35 through 40. I think we're just going to do the odds, but this is talking about blood types. And I thought this was a really good example of like a continuous problem that has you like working with an actual set of data. So if you look at your book, there's a table talking about like what percentage of the population has a certain blood type. And there are different antigens in your blood. There's the A antigen and the B antigen. And then there's also the RH. If you have A, then you have type A blood. If you have B, you have type B blood. If you have both A and B, your blood type is type AB, and you can have both. If you have neither, your blood type is O. So it's just like there are no like type antigens. And then the RH is you're either positive or negative, meaning you have RH antigens or you don't. So RH is there, RH is not there. Okay. So that being said, we are going to analyze the probability, for instance, like if we pick a random person off the street and like test their blood, like what types of probabilities will we find? For instance, 35 wants us to find the probability someone is RH positive. So the way that I solved this problem is I thought, okay, we're given all of this information, but we just want who's RH positive. So I went through and said the probability of somebody being RH positive is the probability of everyone who has a positive. So that's the probability of people who are O positive, plus the probability of people who are A positive, plus the probability of people who are B positive, plus the probability of people who are AB positive. And there is no overlap. We know that there is no A intersecting with B or like O intersecting with B. None of these intersect. AB doesn't intersect with B either, or A. And the reason is because AB is distinct. So you're either A or B or AB. There is no overlap between them. So we would say in terms of this chapter that all of these events are mutually exclusive. You can't be both. Okay, so that being said, I don't need to worry about subtracting anything because they're mutually exclusive events. So I just go and I add everything together and I have 39%, which is 0.39, plus 0.31, 31%, that it's A positive. B positive is 9%, and AB positive is 3%. So I add all of this together and I get the probability of a person that I pick off the street being RH positive as being 82%, 0.82 or 82%. All right, so that was 35 starting off. Let's try 37. Keeping all of this like process in mind, I'm going to give you guys, just like encourage you again to pause the video, go ahead and try 37, see what you think about it, and then we join again. All right, let's give it a try. So we want the probability that there is an A antigen. So that is the probability that somebody is type A. Type A people have the type A antigen. So the probability of A positive and the probability of A negative, because they are separated in this event table. You can't be A positive and A negative. You have to be one or the other. In addition, people who have type AB blood also have the same antigen. They just also have the B antigen. So because we're looking for the A antigen, not just A blood, we can say that this is also the probability of AB positive and AB negative. And so people with, for instance, type AB blood, they can receive blood from both A-type donors, B-type donors, and O-type donors because they have all of the antigens in their blood. That's why AB positive is the universal donor. Not donor, excuse me, the universal receiver for blood types. The universal donor would be O negative. Okay, so we have the setup now. This is all of the types that we have that have A antigens in them. Let's just go ahead and fill in the numbers that we have. So this is 0.31 plus 0.06, 6%, plus 0.03 plus 0.01. And so all of that together is going to equal 0.41 or 41%. Okay. And finally, we're going to do 39, which is what is the probability that a randomly selected person has a blood type that is O or Rh positive? Okay. So what is the probability somebody has type O? Well, there's type O negative and type O positive. So this is the probability for type O. Oops. And then there are the Rh positive groups, which are the probability of A positive, probability of B positive, and probability of AB positive. And all of these are Rh positive. But notice that we only count O positive once. Even though it categorizes into both of these groups, we can't count those people twice. So we're going to put out all of the percentages. So we have 0.39%, or excuse me, 0.39 or 39%. Oh, that was incorrect. I put the O positive down. So this is at 0.09, 0.39 plus 0.31 plus 0.09 plus 0.03. And this all is going to come out to be 0.91, 91%. So a lot of people are type O or Rh positive. What about if we had a person who, or what is the probability that we have Rh negative blood that's not O? Okay, so we have to find Rh negative blood that's not O. We could set it up in the same way. We could say the probability of, oh, this isn't a question, by the way, like in the book, this is just like me like speculating. So we would get the probability of, well, we can't do O negative, but we can do A negative plus the probability of B negative plus the probability of AB negative. Or we could do 1 minus the probability of O or Rh positive. So the probability of being switching up to here, the probability of being Rh negative is equal to 1 minus the probability of being Rh positive. We're forgetting about like the O like distinction right now. And the reason that is because you can either be one or the other, but not both. So yeah. I have a feeling that they're going to like put like a problem like this where they give you like a list of data and then they have you like think about like what's all on this list, like what can I do about this, like how do I organize it? And the best thing to do, I would recommend, is to write everything down. Write down the probability of the thing that, like, write down what you want. For instance, this here, I wanted the probability of RH positive. Write down like all of the individual pieces to that. How do I find this? Do I need to consider, are they mutually exclusive? Ask yourself that question a lot, just so that you like are on like the right page. And then kind of start like playing around with, okay, like how does this work with one another? All right. I would ask for questions now, but there's no one here. So I will remind you all that you can ask me questions anytime on Canvas. My email should be there, and there's you can just comment on one of my announcements or the discussion boards or something. So yeah, feel free to contact me anytime if you have questions about this material. And I hope you guys all have a great day. Thanks for watching the video.